Hi, everyone, and welcome back. It's Kira Garfolo with Greenville Tech's Math 155. Today, we're going to start Unit 3, and we're going to talk about Section 3.1, which is proportions. So congratulations, first of all, you're halfway through the course. Remember, there are 4 units in our course, and you've finished 1 and 2, so now we have 3 and 4 left. This unit is going to shift gears a little bit. We're going to talk about proportions and percents. You've maybe seen some of the beginnings of this, likely not all of it. Then we're going to talk about simple interest, and then we're going to talk about some more complicated loans and interest problems, things that you're going to actually see in real life. So this unit is full of things that you'll actually apply in real life. A lot of people, some of the stuff that you cover in math classes, everybody wants to know, when will I actually use this? And you'll use this unit a lot. So we're going to start with some basic definitions. First, we're going to define ratio. So what do I mean when I tell you that something is a ratio? Really, it's just another word for a fraction. Okay, we're talking about we have a numerator and a denominator. A lot of times, instead of saying, oh, here's a fraction, we're going to word it a little bit differently. We're going to say blank to blank. Okay, so your numerator to your denominator. You're going to want to keep them as whole numbers when you're talking in ratios. Okay, it makes the most sense to talk about in whole numbers. For example, if we have 7 red candies and 18 green candies in a dish, then the ratio of red to green is just 7 to 18, or the way that we often mathematically represent this is 7 with a colon 18. You could also represent this, let me turn the pen on, as 7, of course it doesn't want to write, over 18, okay? So all of these are equivalent ways to write a ratio. Remember, it's just a fraction. So let's get a little bit of basic practice here. Let's say that a classroom has 20 men and 15 women. So what is the ratio of men to women? Well, we have 20 men and 15 women. So men to women is going to be 20 to 15. Similarly, if you're talking about women to men, you're just going to reverse it, okay? So now we're doing women to men, which is going to give us 15 to 20. So notice that we're just reversing there, right? Now, what about women to the entire class? So this is women to women and men. So we need to add those, okay? How many people do we have in the entire class? Well, that's 20 plus 15, which is going to be 35, okay? So it's going to be women is 15, and total is 35. So that's our total women to the entire class. Now in the real world, excuse me, I'm getting over a cold. In the real world, ratios are everywhere. You guys have used them, you've seen them, whether you call them ratios or not, you've used them. One big example that we see in the real world is batting averages. If you guys are watching baseball, you'll hear batting averages all the time, right? And a batting average is just the ratio of the number of hits to the number of at-bats for a baseball player. And usually we're going to express this to 3 decimal places. And even sometimes in sports speak, when you hear the announcers talk, they'll take that decimal, such as 0.125, and they'll make it just 125. Okay, so they'll sometimes drop that whole decimal. For example, what is the batting average for a baseball player who gets 13 hits and 40 times at bat? So our basic ratio is 13 to 40, which is a fraction, is just 13 over 40, so remember it's numerator to denominator. And if we plug that into our calculator, we'll get that this is 0.325, and that's totally correct. But sometimes you might hear this presented as just simply 325. What about the batting average of a baseball player that gets 15 hits and 70 at-bats? You can pause this and solve it on your own. But this was just going to be 15 out of 70, which would be 0.214, or in baseball speak, 214. Okay? Now we can also talk about proportions. And a proportion is created when we have two ratios or two fractions that we're going to compare to each other. They're going to set equal to one another. And this is going to help us. You guys have all heard, proportionally the same or proportionally different. This is going to help us compare those ratios. For example, we might see 3 over x equals 9 over 27. So we know that here we're solving for x, okay? 3 out of how many is the same as 9 out of 27? Or you might see it in that older fraction way of 2 to 3 equals 10 to 15. Typically in this class, we will be using this notation, the equal fractions notation. It's going to make our math a little bit easier. And we're going to use proportions most of the time, like I said, to compare, relatively speaking. Okay, so if you have two different solutions and you want them to have equal concentrations in a chemistry lab, right? If you know that you put however much in 1 liter, how much do you need to put in 1.5 liters? It's going to be these equal proportions, it's equal ratios, and we're going to solve mathematically. The easiest way to solve proportions is to talk about cross multiplying. So when we cross multiply, we set those two fractions equal to each other. So A over B in this case equals C over D, okay? And then to solve, we're going to take advantage of this concept that A times B has to equal B times C, okay? Now remember, multiplication is commutative, so you could also say A times B equals C times B or D times A, any arrangement of those. So you're going to cross numerator times the denominator of the other is going to equal the numerator of that one times the other denominator, okay? This is going to help us solve proportion-based problems. If you're confused by talking about it in symbols, just wait a minute because we're going to do some examples and I think it'll be a little clearer. So for example, we can show that cross multiplying works because we know that 3 out of 10 equals 6 out of 20. And we could prove that. We can show, you could use your calculator to show that they're both going to be equal to 0.3. But sometimes we won't have quite as pretty of math, right? But we can show that cross multiplication works by using the idea that 3 times 20 has to equal 10 times 6 or 6 times 10, okay? And it's going to sure enough show you that 60 equals 60. So your crosses are going to be equal. Now, a lot of times, we're not going to be proving that two things are equal. Okay, you might want to do that in a chemistry lab or to check yourself in other applications. But a lot of times in this class, we're going to be solving for how much do we need of something. And a lot of times in the real world, you'll be doing that as well. So suppose that we know that x over 8 equals 5 over 10. How are we going to solve for x? Well, we're going to extend what we learned in Unit 1. Let's cross multiply these, okay? We're going to know that x times 10 is going to be equal to 5 times 8. And then we're just solving, just like we've done in Unit 1, just like you've done in previous math classes. When you solve for x, you're going to know that 10x equals 40. So what is x going to be? X is going to equal 4. Now you can always check yourself, okay? That's the great thing about proportions. You can check yourself. 4 over 8, if you plug it into a calculator, it's going to be 0.5. And 5 out of 10 is going to be 0.5. So they are, in fact, equal. Okay, this is a great place to pause and solve on your own. I'll give you a minute and then you can resume. Let's solve for x here. 3 over x equals 2 out of 5. So if we cross multiply here, we're going to get 3 times 5 equals 2 times x. We can divide by 2. You could multiply this out if you wanted, but you can leave it all and as long as you're careful with parentheses in your calculator. So 3 times 5 divided by 2 is going to give us x, which if we solve that, it's going to give us that x is 7.5. And again, you could check this. 3 divided by 7.5 will give you the same as 2 over 5, which is 0.4. They're both equal to 0.4, so they're equal. Okay, what about this one? We're going to cross multiply here. So we're going to say x times 100 is going to be the same as 5 times 30. So x is going to be the same as 5 times 30 divided by 100. Which if we use our calculator, that is going to give us that x equals 1.5. Okay, and again, you could check this. You can always check these. It's very helpful. Now that's nice and fun mathematically, but as I mentioned, you've all seen proportions in the real world. Again, you probably didn't call them proportions. You've heard the word proportionally, but maybe you didn't call them mathematically proportions. We use it all the time in chemistry. We use it in cooking. They're used in art a lot of time, or aesthetics. Think about the proportions of the bodies if you're something that you're drawing, or the human body or something like that, if you're a visual arts person. Building and construction, proportions are going to be very important. Maps, you guys have all looked at a map. That's not, true life size, right? It's down to scale. Scales are just proportions. There's so many more that we can list. You'll notice them everywhere. One thing we want to be careful with is units in application problems. Always just remember what you're being asked. Okay? Remember what's being asked. That's going to be your key. Okay. Let's work through some examples now for the rest of this one. You have an 8x10 family photo and you want to print it as a 5x7. Are your ratios of length to width going to be the same, or are you going to have to crop and kind of rescale some things? Well, we can check that. We're not solving for x here, we're just checking. Is 8/10 the same as 5/7? Now, if some of you have worked in photography, you're going to know the answer to this, but let's look at it mathematically. 8/7, or 8 times 7, does that equal 5 times 10? Well, we know that 8 times 7 is 56, and we know that 5 times 10 is 50. 56 is not equal to 50. So that tells us we are going to need to crop. Okay, they're not equal ratios. I think I've overwritten a little bit here. Okay, this is a great place to pause and work some yourself. I'll go ahead. If 2 inches on a map represents 100 miles, then how many miles does 5 inches represent? Well, I always you can put these in either order, by the way. Some people, you could do it as mile over inch, or you could do inch over mile. As long as you're consistent with what's on the numerator and what's on the denominator, you're going to get the same answer. So you're fine. Don't give any stress to that, okay? We know that 2 inches is 100 miles. And we know that we have 5 inches, and we don't know the number of miles. We can set these up as fractions. 2 inches gives us 100 miles, and 5 inches gives us X miles. Now, we can see that if we multiply inches times miles and we divide by miles, inches times miles and divide by inches, it's going to give us miles as our answer. If you like that kind to show that kind, that's fine. But if you're one of the people like I tend to do, I know that my answer is in miles. So I don't worry so much about my units here. Okay. So I know that I'm going to have 2 times X is going to be 100 times 5. Okay. My X is going to be 100 times 5 over 2, which is going to give me 250 miles. Okay, so if 2 inches represents 100 miles, then I know that 5 inches is going to represent 250 miles. If a car can travel 300 miles on 9 gallons of gas, how many miles can it travel on 5 gallons of gas? Well, now you need to pick what you want on top, miles or gallons. I'm going to say, okay, we have 300 miles gives us 9 gallons, or 9 gallons gives us 300 miles, equals how many miles? So X miles over 5 gallons. And here we're going to see that we get 300 times 5 equals 9 times x. So 300 times 5 divided by 9 is going to be x, which is going to give us 166.7 rounded miles. Okay. Now again, you can notice if you had done, it works the same. If you had put 9 gallons per 300 miles equals 5 gallons over x miles, you're still going to get 300 times 5 equals 9 times x. Okay. So it doesn't matter as long as you are consistent in the way that you write it. Gallons on top of miles or miles on top of gallons. Just make sure you do it that way for both fractions. Okay, what about these? The property tax on a car worth $8,000 is $120. So what is the property tax on a car worth $12,000? So for this one, I'm going to say worth over tax. I'm just going to go ahead and write that I'm going to be putting the fractions like that to help me keep it straight. So our first one is worth $8,000. And the tax is $120. And the second one is worth $12,000. And we don't know what the tax is. Okay, so it's going to be X dollars. So by cross multiplying here, we get 8,000X is going to be equal to 12,000 times 120. So X is going to be that 12,000 times 120 divided by 8,000, which if we plug that into our calculator, it is going to give us $180. Okay. Now, if a 200-pound man requires 3,000 calories to maintain body weight, how many calories does a 120-pound man require? Obviously, there are a lot of extraneous factors we're willing to overlook here, but we can still get the idea. We can say, okay, we're going to say 2,000 pounds requires 3,000 calories. 120 pounds requires X calories, because that's what we want to know. So we know that 200 times X is going to be the same as 3,000 times 120. So if we solve that by dividing both sides by 200, we are going to get that X equals 1,800 calories. Okay. Again, if you need to pause, go back, anything like that, go for it. Let's do one more slide of practice for this section. If it takes 200 cookies to feed 50 children, how many cookies would it take to feed 1,000 children? Now this one, be careful, because so far we've said, okay, the bigger numbers go on top, the smallers go on bottom, or vice versa. That's not true here, okay? I would say we're going to say cookies over kids. Now again, you could do it kids over cookies. As long as you were consistent, you get the same answer. So we know that we have 200 cookies for 50 children. Okay. How many cookies? So now we want X cookies for 1,000 children. Okay. So we know that we have 200 times 1,000 equals 50 times X. I am playing my space very well here. So X is going to be 200 times 1,000 divided by 50, which if we plug this into our calculator, we're going to see that it is going to require 4,000 cookies. That's a lot of cookies. Now, usually when I teach this one in person, somebody asks, well, wait a second, couldn't I just see that 200 cookies for 50 children is going to be, well, 4 cookies per kid? So if I have 1,000 kids, I'm going to need 4,000 cookies. Absolutely. You don't realize it, but you're doing the same proportional thinking here. Okay. Show me that work. Okay. You're doing the same thing. Don't just answer on a test 4,000 cookies, because especially if you miss it, I can't give you any partial credit, and that's going to be problematic, right? If I can see where you went wrong, I can help. It's good practice at this point to get in the idea of setting them up as proportions. But again, you're doing the same thought process intuitively a lot of times when we're doing these. It's not as easy when they're not whole numbers, right? Those fractions, or if they're ugly fractions or really big numbers. But sometimes if we see 250, we know that 50 times 4 is going to give us that 200. So each kid must be getting 4 cookies. If that's the way that your brain works, awesome. But again, just show or explain your work on a test. Let's do one more. If 250 milliliters of alcohol is used to make 750 milliliters of a solution in the chemistry lab, how much alcohol do you need to use to make 3,000 milliliters of solution? Now this one, you have to be careful with units again, because everything's milliliters. So instead of saying, okay, milliliter over milliliter, let's just say we're going to talk about alcohol over solution. That'll help us keep it straight, okay? So we know that we have 250 milliliters of alcohol for 750 milliliters of solution. And now we don't know how much alcohol we need for 3,000 milliliters of solution, okay? So we're going to end up with 3,000 times 250 is 750 times x from that cross multiplying, okay? And so if we do 3,000 times 250 divided by 750, that's going to give us x, which is going to give us 1,000 milliliters. Okay, so you need 1,000 milliliters here of alcohol to make that 3,000 milliliters of solution. And again, you can always check. 250 divided by 750 is going to be a third, and 1,000 over 3,000 is a third also. So we know that we're good. In conclusion for this section, remember that ratio is just a fancy word for fraction. And if you're talking about proportions, you're just setting 2 fractions equal to each other. That's going to let us solve for a missing component if we need to. When you're solving those proportions, make sure that you're careful. You're going to be cross multiplying. You want to keep track of your units and keep your units on the top and the bottom the same as the left and the right. Okay, remember we were writing solution or alcohol over solution or cookies over kids. Make sure that you do that. If you reverse one of them, you're going to get the complete opposite answer that you need. Okay, get some practice. There's some great practice in your text as always. Remember, if you need help, what are you going to do? There's the Math Center. There's all kinds of resources in your textbook. There's additional videos in our Blackboard shell. And of course, I'm always available for office hours, email, etc. Don't feel bad reaching out. I'm always happy to help. Thanks for tuning in, and I'll see you next time.